Thanks very much, Steve. It's a pleasure and an honour to be invited to give this seminar. It's a university that can boast not just J.K. Rowling as one of its alumni, I understand, but also, more importantly, Will Young. And I discovered only at lunch with Steve that you also boast none other than Floella Benjamin as your Chancellor. However, the most relevant aspect of Exeter to this talk is that Exeter holds a very special place in British legal history. Now, does anyone know what that might be? What is the special claim to fame of Exeter in British legal history? Anyone? Absolutely. It was the last place where a woman was tried and executed for witchcraft. And the location of the trial of Alice Morland is now a bar called Timepiece in the centre of town. Now, in the last 20 years, my main area of research has been in probabilistic risk assessment. And that has been, as Steve mentioned, in sort of diverse areas from safety critical systems all the way through to things like predicting football match outcomes. And much of the work, especially in recent years, has involved using a technique called Bayesian networks, which enable us to measure uncertainty when there's a scarcity of data, but lots of expert judgment. And it turns out that that approach is especially relevant to legal arguments and evidence, although most of the aspects of the criminal justice system doesn't actually realise this yet. So today, I'm going to explain how probability is actually central to far more legal cases than anybody can possibly imagine, and in particular, involving whenever there's a case that involves any presentation of forensic match evidence, then probability is involved, whether they state it explicitly or not, and in fact, in almost all cases, they get it wrong. Errors of probabilistic reasoning plague the entire criminal justice system, and my argument is that the only rational way of addressing this problem is through this type of Bayesian modelling approach. Now, my presentation is going to be driven by cases that I've actually been involved with, personally, either directly or indirectly. So I'm going to first briefly introduce those. In all the cases, my original motivation was to avoid the common fallacies of probabilistic reasoning, which kind of destroy the potential to properly evaluate the impact of evidence. Now, I'm going to argue, of course, that Bayes, and in particular Bayesian networks, is the only rational way forward for probabilistic reasoning about evidence. But I'm going to explain the enormous cultural rather than technical challenges which stop the more widespread adoption of these methods within the law. Then I'll basically show you how the approach has been applied to the cases that I'm going to introduce at the beginning and make some conclusions, obviously, at the end. Are
you picking up through both mics, maybe?
Second. What about?
Further away as well.
Let me just.
When you look back, it gets clearer.
Is that better?
Looking now.
Is that better? If I go down, it's worse, is it? Okay. So I'm sort of looking down as well. No, it's okay. Now, it seems almost inevitable that any talk on probability statistics and the law includes a mention of this case. Actually, until very, very recently, I would never have mentioned this case, but it just so happens that something very recent has meant that I've actually had to get involved with this. Now, this case is infamous for a probability error that was made by the prosecution's key witness, a guy called Roy Meadows, when he stated that the probability of the defense hypothesis, which was that the two children had died of SIDS, sudden infant death syndrome, was 1 in 73 million. And what he'd done, of course, was to make a classic probability error, which was to assume that the two child deaths were independent. And you look at the probability of a single child death, which is in a family is 1 over 8,500, and when you multiply the two probabilities together, you end up with that 1 in 73 million figure. But actually, that was not the key probability error affecting the case. Most people don't realise that. I'll explain when we come on to this one what the main probability error was that was raised by the probability experts at the appeal. The new thing, and it's only because of this that I would have even mentioned this case, the very new thing is that it turns out they made a fundamental flaw as well. That's very new. Now, in 2007, Levi Bellfield was charged with 2 murders, and that's the 2 murders of Amélie de Lagrange and Marcia MacDonald. It's quite a well-known case, and 3 attempted murders. So there were five crimes charged simultaneously. And he later gained, he was convicted of 3 of the 5 charges. And he later gained even greater notoriety when he was convicted of the murder of schoolgirl Millie Dowler, which I'm sure is a case that many people will have heard of. There were many probabilistic issues in this case, and I was actually an expert advising the defence team in this trial. And another case which will be familiar, I'm sure, to all of you, is the so-called Stephen Lawrence case. And again, most of you will be aware of the aftermath of Stephen Lawrence's murder. Although a number of the defendants, including Gary Dobson here and Stephen Norris, were cleared in the original case, they were tried again in 2011 on the basis of new forensic evidence, namely new fibre evidence and new DNA evidence. And they were convicted. And again, I was involved in this case as an advisor. And finally, oh no, it's not finally. So this is a case, so Mark Dixie was convicted of the murder of Sally Ann Bowman. And in this case, there was exceptionally strong DNA evidence against Dixie. But nevertheless, there was an example of a fundamental failure in the probabilistic reasoning in the case. And my involvement in this was actually indirect, in a way I'll explain, via the Levi Bellfield case. Now finally, and again very recently, I've been involved in reviewing this case. So Barry George was originally convicted of the murder of the TV celebrity Jill Dando. But in 2007, this was sent to appeal, and the basis for the appeal was actually a purely Bayesian argument that might not have been presented in that way. It was basically, the argument was that the key piece of forensic evidence which had led to his conviction had so-called no probative value. So that's something I'll explain. And so consequently, the conviction was quashed as unsafe, sent to retrial without that evidence. Okay, and he was subsequently found not guilty in the retrial and released. But actually, we have now looked at the appeal court transcript, and we feel that, again, there were fundamental flaws in the probability reasoning in that transcript. So, before explaining what the fallacies, the most common probabilistic fallacies are, I want you to imagine, to motivate this, I want you to imagine if in a court of law some evidence depended on the correct answer to the following questions. Okay, what is that very long number divided by that other very long number? What's the area of a field whose length is approximately 100 meters and whose width is approximately 50 meters? Now, just imagine that in the first case, you had to answer that question without the help of a calculator. And just imagine if in the second case, you had to answer that question without being able to use the formula for area. Okay? Now that sounds ridiculous, and actually, in both cases, almost impossible. But that's exactly the kind of constraint that has been applied by the courts for the use of the only rational way of reasoning about probabilities, namely Bayes. And in particular, the two appeal court rulings that have been especially damaging and in places highly irrational are the following. One was in 1995, which was a case of, this was a rape case involving the combination of DNA evidence and other types of evidence, where the judge came to this conclusion, the task of the jury, blah, 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 not to reach a conclusion by means of a formula, mathematical or otherwise, but by applying their common sense. Well, again, think about trying to apply common sense to the previous problems and not being allowed to use the calculator or the formula. And even more explicitly, in the case of RVT, which was a murder case where the main prosecution evidence was a footwear match, and in this case, the judge ruled that, again, no attempt can realistically be made, blah, 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 to use a formula to calculate probabilities. It's quite clear it's out that other than DNA, which is an interesting thing because that's somehow treated as something special, and it shouldn't be. The court has made it clear that Bayes' theorem and likelihood ratio should not be used. Right, so what can go wrong if we're not allowed to use it? What can go wrong? If we're not allowed to use Bayes, what's the problem? Well, what I'll do is I'll take a simple example, very simple example, but the principle is going to be the same for any type of forensic match evidence. Okay. Fred, imagine that Fred is one of a number of men who are known to be at the scene of a crime. And he's just as likely to have committed, just as likely or as unlikely, a priori, to have committed the crime as any of the other people. So our prior belief is that they're sort of all equally likely to have been the person who committed the crime. Suppose that subsequently we discover that whoever did commit the crime, i.e. the real criminal, don't know who that is, let's suppose we found their shoe size, through footwear evidence or whatever, was size 13. And that's quite a rare size. Nationally, that's found in approximately 1 in every 100 men. Turns out Fred matches, because we check him, and he's got size 13. Now, clearly, our belief in Fred's innocence is going to decrease from the prior as a result of finding this evidence. I think everybody can agree on that. Okay? The question is, what is the revised probability of his guilt? Does anyone know what is it? What's the answer? Of course, it absolutely depends on the prior, which in this case can be gained from the number of men who are at the scene. And if you don't know that, you cannot make a conclusion, i.e. the prior belief critically determines what the true impact of the evidence is. It's incredible how many people highly intelligent people fail to understand this point, okay? And failing to understand it leads to, in most cases, to the critical areas, these critical errors of probabilistic reasoning. In fact, what we actually know, so we've got these two statements. So the probability of finding that matching shoe evidence, given that the defendant is innocent, is 1 in 100. That's fine. That's simply expressing our knowledge about the random match probability of the size 13 shoe. Okay, fine. Now look at the second statement. The probability the defendant is innocent, given this evidence, is 1 in 100. That statement is not a statement about the evidence given the hypothesis. That is a very, very clear statement about our belief in innocence, i.e. the ultimate hypothesis here. And what's more, it strongly suggests, it says there's a 1 in 100 chance, well, we know the evidence, there's a 1 in 100 chance that this guy's innocent. Therefore, 99% chance he's guilty. He's almost certainly guilty. Right? Now, of course, the first one is the probability of E given the hypothesis. The second one is the probability of the hypothesis given E. Okay? They're not the same, and yet the prosecutor fallacy is to treat the second statement as if it was the same as the first. Okay? And that, in many, many cases, is exactly what has happened. That's what not just lawyers have done, but also expert witnesses have done. Okay? They've confused the two. And in doing so, Now, look, everybody who has any kind of statistical or probability training can understand the difference between these, okay? But it's incredible how many highly intelligent judges, lawyers, and expert witnesses misunderstand that I fail to understand that these really are different. And of course, if you don't, and you make the second statement when you should have actually only said the first, because it's only the first which is true here, you can potentially really mislead the jury, and that's what the prosecutor fallacy is. Now, of course, the formal way to convince people of what's going on here is to use Bayes' theorem, because what you do is you start with a hypothesis, H, which in this case was the defendant was guilty, say, and we'll have a prior belief about that. So let's suppose that other than the defendant, there were 1,000 other people at the scene. Okay, then it's reasonable to assume that the prior probability of guilt is 1 over 1,001, or the odds are 1,000 to 1 against. Now we get some evidence, in this case the match evidence. We find that he's got the same matching shoe size as that which was known to belong to the criminal. Now what we know is the probability of the evidence given the hypothesis, right? But that's not what we actually want to get to. We want to know what that tells us about how it updates our posterior belief in the probability of guilt, and that's the probability of H given E. All Bayes' theorem does is it gives you the formula for the thing you want to know in terms of the things that you do know or can make some assumptions about. But crucially, of course, you're having to make an assumption about the prior probability of H. And if you plug in the numbers, which I've just given you there, then formally from Bayes, you come out with this revised probability of guilt as being 0.091, which is actually less than 10%. So there's actually a greater than 90% chance he's innocent with those assumptions, which is, of course, a very far cry from the 1 over 100 chance of innocence that comes from the prosecutor fallacy. Now, here's the crux. If you try and show that to a lawyer, even or any highly intelligent lawyer, highly intelligent even forensic experts in many cases, they will not get it. They will not get it from that formula. So, you try and look for alternative explanations, right, about why it is what it is, why Bayes works for that type of example in order to avoid the prosecutor fallacy. So you do something like a population diagram. Here's Fred. He's got size 13. We know he's got size 13 shoes. We know there's 1,000 other people also at the scene. Okay? We know that about 1 in 100 people have size 13 shoe. So about 10 of those other 1,000 people are going to have size 13. So we strip away all the ones we're not interested in, and that leaves Fred as 1 of 11 with size 13 shoe. And that actually means, of course, that there's a 1 in 11 chance that he's guilty, which was actually what we just showed more formally with Bayes, or alternatively, there's a 10 in 11 chance that he's not guilty. And again, that's, of course, to be compared and contrasted with the 1 in 100 chance of innocence that was claimed from the prosecutor fallacy. I mean, there are other kind of visual equivalents to that sort of population diagram that you can use to try and explain this. You start off with 1,001 people, use a decision tree. You've got the defendant, you've got the others, you do the tests, you do the matching tests. Obviously, Fred matches the one there, 10 of the 100, 10 of the 1,000 match, and you compare the ones that match and you get the same result. Okay, 1 out of the 11. Fine. So it ought to be simple. You ought to be able to do it, with these arguments. The problem is that these sort of arguments are very, very difficult to scale up when the evidence becomes a bit more complex, as I'll show. Okay? But just to give an indication of how extensive the problem is, I just picked this out as one of many examples. Actually, you more or less would find it difficult if you read the kind of the legal reports in cases where there's sort of forensic evidence. Every week you'll see something like this. I've picked it out because it's from Stephen Lawrence trial, where it's reported, it says, a stain on the murder-accused jacket was caused by fresh blood with a 1 in a billion chance of not being victim Stephen Lawrence. That is the prosecutor's fallacy, because what the evidence was in this case was that the chances that you would get that evidence if it wasn't from him was the 1 in a billion. And that's not what this says. This is making a direct statement about whether it was his or not, okay? Not about the chance of seeing the evidence if it was or wasn't him. And what you also should need to realise is it doesn't require an explicit statement of probability and statistics for you to commit the fallacy. Right? I have personally seen or heard dozens, probably many dozens of statements like this normally by lawyers, but sometimes by a forensic scientist. They'll make this sort of statement. The chances of finding this evidence in an innocent man are so small, well, that's fair enough, that's the probability of E given H, that you can safely disregard the possibility that this man is innocent, i.e. they're treating them as equivalent, okay? That the probability of H given E sort of is the same or similar to the probability of E given H. It's very small. It's so small that you can discount it, okay? There's no explicit probability statement in here, okay? It doesn't give you the exact numbers, but it's making the same fundamental error. So you can say, well, but DNA evidence different, right? This is the argument. In fact, we can even point to case law, which even suggests that there's got to be this difference, right? That it somehow doesn't matter if you make the error for DNA. Why? Because the very low random match probabilities. If you've got, a very low match probability, like 1 in a million or 1 in a billion, as you do sometimes get with DNA, the assumption is that that's so low that it somehow doesn't really matter if you don't take account of the prior. But of course, it always matters, right? Unless the prior is actually 50-50, that's the only time it won't matter, right? And sometimes it can matter dramatically. If for example, the DNA, if it's a 1 in a million, just imagine it was a 1 in a million DNA match, but suppose you actually had a database of 20 million people and you actually did a search for the first person who matched in the database, and you can see how incredibly wrong it is to assume that there's a 1 in a billion chance that this is not your guy. Okay, it's of course ridiculous in that case. But actually, what's more worrying is that in many cases where you hear about, DNA match, it's a fair cop, that's your man, right? It turns out actually it was a so-called low template DNA match, where actually the random match probability here can be as high as 1 in 100. It's not your 1 in a billion, it's 1 in 100. Okay, and in that case you can see massive implications of not taking account of the prior and committing the prosecutor fallacy. But it turns out it's even worse than that, because in all cases, there will be probabilities of testing errors, false positives and false negatives, which can occur at any stage in the process. How do you even know that the DNA you got from the scene is the one that you tested, that got into the lab? How do you know it didn't get contaminated? How do you know your test equipment is perfect? Right? Defense and prosecutors actually use the same type of test equipment. Okay? What if it turns out that these tests are not perfect, though you have small probabilities of errors, both for false positives and false negatives. They're never taken into account, and I'll explain why in a minute. Right? And not taking them into account completely blows apart most of these the probabilistic conclusions that people make. And this actually applies, this applies to all types of forensic match evidence, what I'm telling you here. Now, to kind of counter this, of course, probability experts have said, well, there's a way around this, to avoid this type of thing happening. And the way around it is to completely separate out the prosecution likelihood, to focus on that. What's the probability of seeing the evidence if the prosecution hypothesis is true, which in our case would have been 1, against the defense likelihood, which is the probability of seeing the evidence if the defense hypothesis is true, and that's the 1 in 100 that we saw. Because if you then use the likelihood ratio, which is simply the prosecution likelihood divided by the defense likelihood, which is 100 in the example, then it turns out, providing certain conditions are true, are valid, like providing that these hypotheses are sort of the inverse of each other, guilty, not guilty, providing those are true, and that's a very, very important assumption, right? Then it turns out actually from Bayes, which I'll show in a minute, you can make these assertions about the probative value of evidence. If the likelihood ratio is greater than 1, it supports the prosecution case, right? And the greater it is, the more it supports the prosecution case, right? And if it's less than 1, it supports the defense case, and the closer to 0 it gets, the more it supports it. And crucially, if the likelihood ratio is 1, it has no probative value. It neither supports the prosecution nor the defense argument. Great. Why do forensic scientists love this? This has been really pushed heavily. They love it because actually it appears that you never have to consider the prior. You're never forced to consider the prior here. You just come up with this likelihood ratio, which is a number independent of the prior, apparently. Right? And of course, forensic scientists and lawyers don't like to think about the prior. So here's a way of saying, they can say there are sort of tables they can use. You know, if it's between 100 and 1,000, they'll say that strongly supports the prosecution case. They'll use things like that, these verbal scores. But there's a problem. In fact, there are two fundamental problems. One is that they often ignore that requirement, and we'll see that leads to errors of reasoning. And the other is that actually the only way this makes sense, the only way that this works is because actually it is Bayes' theorem. It's the odds version, it's the odds form of Bayes' theorem. It works because Bayes' theorem tells you that the posterior odds is simply just the prior odds times the likelihood ratio, right, under the given assumptions. And actually, to make sense of it, you know, you've still got to consider the prior odds, right? So in our example, we started, remember, with the prior odds, it was 1,000 other people. So the odds in favour of the defence were 1,000 to 1, okay, in favour of the defence. We now multiply it by the likelihood ratio, which is 100, and we end up with posterior odds of 10 to 1 still in favour of the defence, which again is the same thing we observed before. And so that seems to be, in this case, we can say, well, it supports the prosecution case, but it's still almost certainly, you know, still almost certainly not guilty on the basis of that evidence alone. But if the prior odds were only 4 to 1, if there was only 4 other people at the scene, and we don't know anything about those other people, then with exactly the same evidence and exactly the same likelihood ratio, we end up with posterior odds which actually strongly favour the prosecution case by 25 to 1. So to imagine that you can use this still without thinking about the priors is, of course, completely ridiculous. To show how ridiculous as well, if you don't get the assumptions about the idea of having to have alternative hypotheses which are the inverse of each other, take this example. So this is, of course, the game Cluedo, and we've got 6 characters, 3 of whom happen to be women, 3 of whom happen to be men. And in this case, the prosecution hypothesis is that Mrs Peacock is guilty. Okay? Now let's suppose that the evidence, we've got some evidence that the murderer was a woman. That's our piece of evidence, right? Is that evidence probative or not? Right? Does it support the prosecution case or not? Well, let's apply the formula. If we assume that the defense hypothesis is that Mrs Peacock is not guilty, which is what you should do, then you can use this approach and you'll find out that the probability of E given the prosecution hypothesis equals 1, the probability of seeing the evidence if she's not guilty is 2/5 because 2 of the other 5 are women. Okay? That gives you a likelihood ratio of 2.5, which does indeed supports the prosecution argument. It's definitely probative. Now, a cunning defense lawyer will do the following. They will cherry pick. Instead of choosing what is the only rational defense hypothesis, which is not guilty, they'll pick something, a subset of it. And this is not just fantasy. This really happens, right? But of course, it looks ridiculous here, but it's an example of what really happens. They'll say, well, no, I'm going to propose that the defense hypothesis, someone else did it. And I'll say Miss Scarlett. I think Miss Scarlett was the murderer. I don't have to offer any evidence for that, but that's all I'm prepared to say. That's all I'm prepared to concede. That's the defense hypothesis. If that's your alternative hypothesis, if you try the likelihood ratio approach, you end up with a likelihood ratio of 1. Because in that case, the probability of E given that hypothesis is 1 as well. And if the likelihood ratio is 1, you can say this evidence has no probative value, therefore it's formally inadmissible. Okay? But of course it wasn't. It's just because of the way you've actually phrased that defense hypothesis, it's the kind of cherry picking, isn't it? And that brings us, in fact, to the Sally Clark case and why there's a new flaw in the way the probability experts did the reasoning. Because what they did was they compared that so-called that mythical prior about whether 2 babies could die of SIDS, the 1 in 73 million or whatever, assuming independence. But actually, even if you assume dependence, it actually is still a very low number. It's actually 1 in 11 million, okay, with certain reasonable assumptions. So actually, now you can see why that on its own wasn't really a very strong case as to why she was wrongly convicted. The real case is to say, well, let's look at the alternative hypothesis. If we're going to do that, look at the prior for the defense hypothesis. What's the prosecution hypothesis? And what the experts said, it's a correct strategy to do it this way. Say, well, we've got to compare it with the probability that she murdered her 2 babies. Okay? And one of the probability experts, a Bayesian guy in the appeal, said this. He said, well, the prior probability of HD that Sally Clark, the 2 babies died of SIDS, was 100 times greater than the probability. Oh, I've got that. Sorry, I've got this the wrong way round. Sorry. It's the probability of, actually that should be, it's HP, just to confuse it, sorry. That's the probability she murdered her, that she actually did murder the 2 babies, is actually 100 times greater than the probability of the 2 babies dying of SIDS. So if you look at the evidence, if you assume that the evidence, all the medical evidence, let's suppose he said, let's assume that's got a likelihood ratio of 5, then what can you conclude from that? He concluded that the posterior probability still favoured the defence hypothesis, which, yeah, the other way, still favoured the defence hypothesis of SIDS rather than murder. Because it's 100 times, even though the likelihood ratio is 5 times in favour, you end up 20 times more in favour of the defence hypothesis. That was the argument. Turns out it chose the wrong hypothesis. The correct prosecution hypothesis is not that she murdered both her babies, but that she murdered at least 1. Right? There were certain other assumptions you need to make, but that was what it should have been compared against to be the completely fair argument, to be able to use the likelihood ratio approach. Turns out, using that expert's exact same assumptions on the statistics, you end up with the prior probability, again, I got that the wrong way round, of the prosecution hypothesis being only 2.5 times greater, not 100 times greater, only 2.5 times greater than the defence hypothesis. And in that case, if you assume the same likelihood ratio of 5 for the evidence, actually, you end up with odds of 2 to 1 in favour of the prosecution hypothesis, not the defence hypothesis. Now, this was all, I'm not saying that this should have been revisited or anything like that, but there was a flaw, this fundamental flaw, in the arguments that were used by those probability experts after all of the kerfuffle about the problem with the probability and statistics. And I mean, it's just the tip of the fallacies iceberg. I mean, here's some examples of common fallacies which are discovered. In fact, all of these, except the first one, they were not only committed in the prosecution open in the case of Levi Bellfield, but some of them were committed many times. But while Bayes can help explain and avoid these kinds of fallacies, we've got this scaling problem. What is the scaling problem? Well, it's all very well saying that that's your sort of basic case where you've got a hypothesis like your defendant was the source of the DNA, you've got the evidence that his DNA matches that found at the scene. You can do, using the sort of techniques I've just shown, the visual ones, you can work out using event tree or whatever, you can work out what the correct probabilistic conclusions are and avoid the fallacies. Fine. Actually, that's an example, of course, of a 2-node Bayesian network. In a real case, this is what a Bayesian network will look like. You can have multiple different hypotheses from the defence and the prosecution, multiple related bits of evidence, And for this, you can't rely on doing it by hand. You need a Bayesian network tool to do that for you, which is exactly what they do. You need the specialist tools to do it, to work it all out. But actually, even in the case of a single piece of forensic evidence, it is not a two-node Bayesian network. It's something more complex. Because, as I said before, as soon as you consider the possibility, which you have to, that there could be false positives and false negatives, this is your network. Okay, that's the network, right? The only things that you actually observe are this and this. These are all really unknown. Okay, so you have to do the probability calculations, again, using this type of Bayesian network. If you wanted to do it and get the argument across without somebody understanding Bayesian inference, right, you'd end up doing something like an event tree. And here's the event tree for that model. That is it. In fact, actually, this is the first. We've just written this up in connection to the Barry George case. And actually, I believe this is the first time anyone has even done the proper probabilistic analysis of the simplest case of match evidence, taking account both types of error probabilities. It's disastrous. The reason why they never did it, why the experts never bother with this, why they simply ignore the potential for errors, is because this is what they'd end up having to do, and they don't do it. It's really hard to explain. You can't expect someone, to simply see that and grasp it as why it's true. Even worse is where you'll get a mathematician, a Bayesian, brought in to try and explain it from first principles using a formulaic approach, which is exactly what happened in the Adams case, which was one of that case where that first example of the appeal court criticising the use of Bayes. That's what the defence did. They basically tried to get the jury to understand a full Bayesian calculation formula, a complete waste of time. And in my view, the only way round this is to basically apply what I call the calculator analogy, which is that, a court would certainly be happy to allow a calculator to do something like the long division example. Okay, what they wouldn't do is say, well, okay, you can do that, but you've got to explain all the underlying, thousands, millions of circuit-level calculations which are going on in order to arrive at that result. It would be ridiculous, wouldn't it? You've got to get across that same idea. Bayesian network technology and the algorithms are sufficiently mature. There are enough tools out there and verified algorithms that you shouldn't have to then look at what goes on underneath. You wouldn't expect to explain the results of that by actually looking at the underlying Bayesian, theory, all of the calculations that go into it. Hopeless, right? And that's a very simple example, but that's the calculations needed. You've got to basically take this on trust eventually in much the same way as you do trust the results of a calculator. And in fact, if you look at that case of the match evidence and run it through a tool, this is with the assumption that you've got a 1 in 1,000 random match probability for some, let's say, DNA evidence. And this time we assumed at the start that it was 50-50 whether the target was the source. When you enter the evidence that you've got the match here, assuming perfect test accuracy, no probability of errors, you end up very, very strongly believing that the target is the source when you run it through. But if you just tweak it, if you change it and allow for a false positive rate of 0.1, a false positive rate, negative rate of 0.01, it's a relatively small, probabilities of errors. Exactly the same evidence leads you to a completely different belief about whether the target is a source. Much more massive uncertainty there. And so what I've suggested is not without major challenges. First of all, when you're dealing with lawyers, you hit this problem. You'll get lawyers who say, actually, I don't want anything to do with probability. There's no such thing as probability, right? The number of times a lawyer has said that, you wouldn't believe, right? A number of times a lawyer has said something like the following. Look, the guy either did it, in which case there's a probability of 100% that he's guilty, or he didn't do it. So there's a 0% chance. So either one or the other. You can't have something in between. There's no such thing as probability. Okay, that's the argument. And of course, this fundamentally is a misunderstanding about the notion of uncertainty. then you get the one, you know, this obsession about not being able to combine subjective evidence with objective. But actually, and they say, well, you know, DNA is objective, so it's fine, blah, blah, blah. But in actual fact, as I pointed out, even DNA evidence actually involves a lot of subjective assumptions which are not properly articulated in the calculations. And then you've always got the classic problem. You've always got to define some subjective beliefs, like about the priors. It's a problem. It is a problem, not denying it. The big challenge is actually getting consensus from other Bayesians, right, who are kind of, you know, don't want this stuff to be sort of used within the law. There are plenty of people like that. What you actually, my view is that what you need to stress are things like, of course, you've got these subjective assumptions in a Bayes net, right, the priors and the conditional probabilities, but fine. Let's argue about those. Let's make clear what those assumptions are, but don't worry about whether the calculations are correct, because we know they are. Okay, focus on those. Just focus on the assumptions, right? And that way you can incorporate this subjective expert judgment. And in fact, the way you can actually address many of these concerns is to look at a range of priors. So, for example, we were involved in a medical negligence case where we ended up very successfully doing the following. We said, look, what's the claimant's prior and what's the defendant's prior here? What's the limit here? And using the evidence we had and that range of priors and ran it through the model, actually, it always pointed to a particular risk, which was sort of, you know, either way you did it, which actually was in favour of the defendant's claim. So you can do it. It's not easy, but it can be done. And using these types of models, you can easily show the results of different assumptions. But, you know, you've got to see it as a calculator. So moving towards the kind of the conclusions here, we now go back in summary to what we've done in the cases that I mentioned, what we actually did. So in the Barry-George case, as I said, in the original trial, there was this hypothesis, right, which is the defense hypothesis that Barry-George didn't fire the gun. Okay? The key piece of forensic evidence was this firearm discharge residue evidence. That there was a particle of that found in his coat pocket. Now, in the original trial, the firearms expert gave a statement about what was essentially the defense likelihood. He didn't give a probability. What he said was, when he was asked about how likely it would be to find that particle if Barry-George hadn't fired the gun. And he said, very unlikely. Now, if you don't back that, if you don't also give a prior, and if you also don't give the prosecution likelihood, in isolation, it's easy to see how the jury could be misled into thinking that meant, well, that's a very low probability that he didn't fire the gun, therefore there's a very high probability that he did. You can see it could be potentially misleading. Subsequent to that, a guy called Ian Evett, who was a probability expert at the Forensic Science Service, said, well, look, they never considered the prosecution likelihood in this case, and they should have done, right? What he did was go back to the actual expert himself who presented at the trial and said, look, I want you to give me probability estimates for these two things, the defense likelihood and the prosecution likelihood. And what he basically said was they're both about the same, 1 in 100. So it's just as unlikely that you'd find that particle of FDR in his pocket if he fired the gun than if he didn't fire the gun. That was a very successful argument because that was accepted, right? Because the likelihood ratio is 1, has no probative value. But it turned out, in our view, it's just been published in the Science and Justice journal, that argument was flawed, right? Because actually, when you look at the trial transcript about what probability the expert was really giving, yes, he was giving the probability of seeing the evidence if Barry-George did fire the gun, that was the 1 in 100, but when he gave the 1 in 100 for the defense hypothesis, he wasn't giving it for not fired the gun, but for something subtly different. He was thinking about how it could have got there. What was probably it could have been the integrity of the coat could have been corrupted. And of course that could happen at the same, these things could both be true, right? Neither of them could be true. The point is that they're not mutually exclusive. They're not, one is not the negation of the other. And it's only when one is the negation of the other that you can conclude that this evidence doesn't have probative value. So even though the probability of E given this true is 1 in 100, and the probability of E given this true is 1 in 100, when you shove this in, when you observe that evidence, actually the probability of HP increases. So, and we looked at it under different scenarios. It was actually a slightly more complex Bayesian net model needed, but that gives you the kind of idea of what was involved. And in the case of Bellfield, we were originally brought in sort of a classic, almost combinatorial argument. There was some number plate match evidence. It was the only hard piece of evidence against Bellfield in all of those 5 crimes. The only piece is that they claimed to have his number plate from the scene of one of the crimes, but it was a partial match. Okay, it was from a very fuzzy image. Blah blah blah. We were asked to analyse the probability that it really was a match, and it was actually a very low, quite a low probability. Okay, that evidence actually was seriously discredited at the trial. That number plate match evidence, not just from our. There was another expert with a different perspective also discredited that evidence, but. Unfortunately for Bellfield, fortunately for justice, whatever, there was a massive amount of circumstantial evidence against him, right? But of course, the defence, having seen the prosecution opening statement, sensed, had a very good understanding, actually, that there were lots of probabilistic fallacies in here, asked me to look at that as well, and that's when we found this ream of fallacies, okay? And he actually, the barrister based the entire defence on that type of argument, right? Bellfield was still convicted of 3 of the crimes, and 2 of the others he was found not guilty of. The good news from a justice perspective, right, is that the judge accepted the arguments that we'd made about the probabilities of the probabilistic fallacies in the prosecution's statement, and instructed the prosecuting QC, instructed them he must not repeat any of those in the closing statement. Again, in the case of R.V. Dobson, it was about the probabilistic flaws in the forensic reports, sort of revealing some issues under cross-examination of the experts. The good news is that whereas I showed you that example from the BBC and many other papers reporting that the prosecution expert had made the prosecutor fallacy, in actual fact, he did not make that fallacy in court. What he said was the correct thing. He gave the probability of the evidence given that it belonged to Stephen Lawrence was 1 in a billion, not as was stated by the BBC and all the other media outlets. But here's a concern. Whoever wrote those reports, all the people, the reporters, some of them are legally trained, they were sitting in court and still interpreted it in the wrong way. And if they interpreted that way, is it possible that the jury interpreted it in the same way? Now, over 20 years ago, an influential American evidence expert made this quote when he sort of discovered the potential Bayesian networks. He said, "I assert that we now have a technology that's ready for use not just by the scholars of evidence, but by trial lawyers." Sadly, that optimism was misplaced and unrealistic. What I've shown is that correct probabilistic reasoning is central to lots of cases, including, the famous ones are just the tip of the iceberg. That's for sure, right? As I said, they include every case where forensic match evidence is presented, either explicitly or not, in probabilistic terms. And unfortunately, errors plague the criminal justice system. And even more unfortunately, sometimes, as I've shown, in at least 3 of the cases, Bayesian experts actually compound the problem by making their own mistakes, either genuine probabilistic mistakes or making the mistake of trying to explain Bayes from first principles in court. And that discredits it just as much as anything else. Doing it correctly requires Bayesian nets, but the court is not the place to be showing Bayesian networks. It's about analysing the pre-trial evidence, convincing the lawyers and the experts about the value of the evidence, etc. And not doing it from first principles, but instead focusing on this calculator analogy. Give them a simple example like the population diagram in the simple case to show them this is how Bayes works, and getting the rest on trust. Okay? It's not easy. It's not easy. Just get them to focus also on just the things that really are open to debate, like the priors, the subjective priors. Now, I believe that in 50 years' time, professionals, all kinds of professionals involved in the legal system, will look back in total disbelief that they could have ignored these available techniques for reasoning about evidence for so long. Thank you.